Hi, I'm Tom Gomersall. I'm from BTL, creators of the Surpass platform, and I'm going to talk a bit about IRT scoring, or item response theory scoring, which is our new feature in the latest release of Surpass. So IRT scoring, or as I said, item response theory scoring, is a more advanced version of scoring exams. It's not just a case of adding together the marks for the items in the test. It takes into account the difficulty of the items that were answered correctly and the items that were answered incorrectly. So the reason for this, the main thing is to be able to compare the performance of candidates who've done different lists of items in their test. So in the new LOFT, which is linear on-the-fly testing, functionality we've got, you can define rules that enable you to deliver equivalent tests to candidates, but they don't all get the same items, so that the exposure of the items is controlled. So in this case, you can get the IRT score, and those scores can be compared for different candidates despite the fact that they won't have seen exactly the same sets of items. So just as an introduction to item response theory, we'll have a look at the item information function. So this is the way we measure the performance of an item, or how we expect it to perform in use in real exams. Or there are up to 3 parameters that define an item or its model for item response that for IRT, which are A, B and C, which you can see in the function here. So we've got the probability, which is probability of getting the item correct for a given level of theta, where theta is the ability of the candidate. So candidates of low ability would have low values of theta, probably negative, and then candidates of high ability would have high levels of theta. So it's an arbitrary range, which is only meaningful in the context of an exam. So it's not got any units, but it goes negative to positive, often in the range -4 to 4 or -2 to 2. So in the function, we've got 3 parameters, A, B and C. So B is the most important one, which is the difficulty of the item. So that tells us how hard it is. So a high value of B would mean a more difficult item, and then an easier item would have a lower value of B. A is the discrimination of the item. So that tells us how well it discriminates between candidates of varying abilities. So effectively how steep this curve is, which is the curve I'll speak about in a minute. And then C is the pseudo-guessing parameter. So that tells us how likely a candidate of very low ability is to get that item correct. So effectively, how likely are you to get it right if you guess? So if you had a 4-option multiple choice question, then the likelihood of getting that right if you guess is 25%. So you'd have a C parameter value of 0.25. So this function brings us on to the chart here, or the graph, which is a graph of the function for varying levels of theta or ability. So down here we've got -2 or low ability candidates up to +2 or high ability candidates. And then on the vertical axis we've got the probability. So this is the probability of a candidate of that ability getting the answer right. So we can see that for low values it's a low likelihood of getting it right. So this would be 0 down at the bottom. And it varies all the way up to 1, which is obviously 100% likelihood of getting the answer right. So as theta increases, or ability, the likelihood of getting it right increases up to very high levels of theta, where it gets close to, but never actually reaches 100% likelihood of getting the answer right. So we'll talk about how this then goes into working out the candidate's ability based on their answers to a whole list of items in a test. So if a candidate's done very simple test in this example, maybe a 4-item test. In reality, that would be more like 50 or 100 items. But to enable us to draw it on the board here, we'll say it's just a 4-item test. So, say the first item, we'll draw the item response function for an item the candidate got right. So it would look something like this. And then the second one that the candidate got right might be a slightly more difficult question. So that would end up with a curve like this. And we can see that because it's more difficult, it's shifted to the right, so the likelihood of getting it right for a given level of theta is lower because it's harder. But then there are other questions in the exam that the candidate got wrong. So we want to draw the function of the likelihood of the candidate getting that item incorrect rather than correct. And because in the IRT scoring we've got, it's dichotomous. So every item is either right or wrong. There's no in between. So if you know the probability of getting it right, then the probability of getting it wrong is just 1 minus that probability because they add up to 1 or 100%. So the curve for the probability of getting it wrong is just this curve here flipped round, so it's 1 minus that. So for item 3 that the candidate got wrong, the curve would look something like this. So it starts off, low ability means high probability of getting it wrong, going to high ability candidates who have a low ability of getting it wrong. A low likelihood of getting it wrong. So it would look like that. And then there's another question, slightly easier one, so that he also got wrong, and it's got a curve like that. So we've now got 4 items on our chart, 4 lines. So we can say for each level of theta, these are the probabilities of the outcomes for each of the 4 items. But with probability, if 4 events happen, or you're looking at the probability of 4 events happening, you can multiply those probabilities together to get the overall probability if they're independent events, which they are in this case. So if we can take all 4 of these curves, multiply them together, we can put them onto another curve which gives us the overall probabilities of the outcome that occurred. So for all 4 items, or in the case of a real exam, all 100 items that could be taken. So if we were to multiply all these values at, say, -2, we'd see that it's probably going to be a low value because we're multiplying by 2 very small values. Similar situation up here at the high ability, we've again got some very low values, so we're multiplying by 2 small values, we're going to get a small value. But then in the middle, we're going to get some higher values than that because we haven't got the such small multipliers in there. So in practice, what you get is a curve that looks something like this. So what we can see is it peaks somewhere on the theta scale. So the likelihood of a candidate with -2 ability of getting this outcome is low. We could say the same about a candidate of ability +2, also very low. But somewhere there's a peak. And this is how we do the IRT score. So we look at this curve and we can say there's a peak here. Now the actual probability itself, we're not really interested in that. The important thing we do want to know though is at what level of theta is this peak. So we can say that the maximum likelihood theta to give the outcome that we've got, so these 2 questions right, these 2 questions wrong, would be this level here. So we can give the candidate, in this case, a theta value of 0.6, which could then be compared to other candidates who've done other lists of items, but not necessarily the same items as this candidate. And we could also work out IRT domains. So if you've got groups of items for which you want to generate an IRT score, you can do that, and you can compare those scores regardless of how many items there are in those domains. You could define your pass mark or grade boundaries in terms of theta. So that if, in the example we've given here, the pass mark or the passing score could be 0.5, which would indicate, in our scenario, that the candidate has passed because the IRT score is greater than 0.5. So we've talked a bit about IRT scoring. So if you want any more information, then please get in contact with the BTL Surpass team, who'll be more than happy to help you with any inquiries. Thank you.